Welcome to qnawire.
Hi, answer the following 6 questions. The first one is for a weak acid or buffer, why is the half equivalence point important? For the first one, the answer is that the pH at half of the equivalence point is going to be equal to the pKa. This is given because pH is equal to pKa plus logarithm of the concentration of the conjugate base divided by the concentration of its associated acid. So at the equivalence point, both of these guys are equal, so the logarithm of 1 is equal to 0 and pH is equal to the pKa. For part 2, what is true at the equivalence point of the titration of a weak monoprotic acid? Why is the pH above 7? So first of all, the pH at the equivalence point is going to be given by, for example, let's say that I have a weak acid HA that is going to be titrated with a strong base, generating the conjugate base plus water. So at the equivalence point, the pH is given by a solution, assuming that we start with an initial concentration of C0, well, with an initial amount of mole of N0 actually, of a concentration of NO divided by total volume at the equivalence point of A minus of the conjugate base. So since the pH is given by the solution equivalent of the conjugate base of the acid, the pH needs to be higher than 7. Next up, on 3, why should dilution of a buffer with pure water not change the pH? This is because if we go back to the Henderson-Hasselbalch equation, remember that this is the concentration of A minus divided by HA, right? The conjugate base divided by the acid. If we change the volume, the amount of mole that we have is actually the one that is going to be telling us how this ratio behaves. Recall that this part is equal to the concentration of A minus divided by HA. So if we change the total volume without altering the amount of mole of each of the species, it doesn't matter, both of these guys are going to cancel. So a dilution is going to keep the pH of the buffer. Next up, for question 4, why would a mixture of NH3 and NH4Cl constitute a buffer, HCl and NH3 constitute a buffer, but NaOH and NH3 would not constitute a buffer? So first of all, for a solution of NH3 to be able to be a buffer, we need to have the pair NH3 NH4 plus. So both of the species need to be present in solution. So in the first case, when we have NH3 plus NH4Cl, we are going to have both of them because this salt in solution is going to generate NH4 plus Cl. On the second case, we're going to have NH3 plus HCl. The reaction of these reagents is going to produce NH4 plus Cl minus. So we have the pair NH3, NH4 plus. And finally, NH3 is not going to be able to react with the hydroxide, so that is why the last one is not going to constitute a buffer. Following this, for question 5, we are asked if a combination of HCl plus NaOH is going to be a buffer. The answer is no, because both of these substances is a strong acid combined with a strong base. So the reaction between these guys is producing water plus the salt that is going to be dissolved in water. And finally, for part 6, we are asked why calcium carbonate is more soluble in HCl than in pure water. So let's look at what would happen after we have the solubility product of calcium carbonate. We're going to generate calcium plus carbonate, calcium 2 plus, carbonate 2 minus, right? So what is going to happen is that the carbonate 2 minus can react with the additional hydrogen ion to generate HCO3 minus, and in turn it can react again in order to generate carbonic acid. Depending on the pH of the solution, the equilibrium is going to be shifted towards one place or another, but the fact that the carbonate can react is going to produce a common ion effect and increase the solubility of calcium carbonate. Remember that the solubility is given by the solubility product, that is concentration of calcium 2 plus times concentration of carbonate 2 minus. If the concentration of the carbonate decreases because of the presence of an acid that allows this reaction, what needs to happen is that the concentration of calcium needs to increase in order to maintain the solubility product constant. And that would be all for this problem. Thank you.